Welcome to Chem 1A at Shasta College. This is a Chapter 2 screencast dealing with some aspects of John Dalton's atomic theory. If you allow magnesium and oxygen to react with each other, what ends up happening is you get a very, very bright flame being produced. Here's a picture of a piece of magnesium metal burning in the presence of oxygen. It takes a little bit of a flame to get it started, but once started it burns very vigorously, and it produces a compound called magnesium oxide, which looks like this. It's sort of a white powdery solid. And if you do very careful measurements of experimental data, what you find is something like this. Here's some sample experimental data. If you take a 1.157 gram piece of magnesium and allow it to completely burn, it will react with 0.762 grams of oxygen, and it will produce 1.919 grams of the compound magnesium oxide. Now notice, of course, that the total mass of what you started with, the magnesium and the oxygen, is equal to the total mass. In this case, there's only one substance that's formed, but it's equal to the mass of the magnesium oxide that is formed. And this is a fairly general situation. In fact, it's a completely general situation. The mass of the starting materials, the starting stuff, and our term for that is reactants, and the mass of the ending materials or ending stuff, which we call products, are equal to each other. And this is true in general. The relationship when our material we start with and we end up with have the same mass, that's going to always be true for a chemical reaction, and we call this the law of conservation of mass. Now, this might seem fairly obvious to you, but it wasn't necessarily obvious hundreds of years ago in the day of John Dalton, and he not only was instrumental in summarizing several laws, including this law, but in starting to develop the atomic theory. And so in this screencast, we'll just talk about a couple of the other things that are maybe a little less obvious than the law of conservation of mass. We also find if we burned a larger piece of magnesium, it would react with more oxygen, and the compound that's formed, we'd make more magnesium oxide. But any sample of magnesium oxide always ends up containing oxygen and magnesium in a 1.52 grams of magnesium to 1 gram of oxygen ratio by mass, or this is true in whatever mass units you use. And the reason for this is magnesium atoms have a mass that's about 1.52 times greater than oxygen atoms. So if we have more or less of the substance, the ratio of the magnesium to oxygen masses are always the same. Same thing's true for any other substance. All samples of water contain hydrogen and oxygen in a 1:8 ratio by mass. Oxygen is 16 times more massive than hydrogen, but there are 2 hydrogen atoms for every 1 oxygen atom. There's where we get the 1:8 ratio. And this is true if we have a little water or a lot of water. Same ratio. And this is true for a bunch of different carbon-hydrogen compounds, like octane. It's C8H18, the chemical formula, and all samples of octane, whether you have a little bit of it or a lot, and it's found in gasoline, they contain 5.33 to 1 ratio by mass of carbon to hydrogen. And this generalization, that any sample of a given compound, a specific compound, always contains the same proportion of the elements in it by mass, is called the law of constant composition, and it's also referred to as the law of definite proportions. So a given compound has a definite composition, a definite proportion. Now, also worth noting is that we can have 2 elements combined to make a compound, and sometimes the same 2 elements make different compounds. And a classic example, of course, is carbon and hydrogen, which make tremendously large number of compounds between them. These are just a few. Methane gas is a 3:1 ratio of grams of carbon to grams of hydrogen. Propane gas, C3H8, is a 4.5 to 1 ratio. C4H10 or butane is a 4.8 to 1 ratio of mass of carbon to mass of hydrogen. Octane, which we just talked about, 5.33 to 1, and so on. And this is, carbon and hydrogen is kind of complicated. There's so many different possibilities. So let's do something a little simpler, which is copper and chlorine. And it turns out that copper and chlorine can make a kind of green crystalline solid, shown here, represented here at least, which has a mass of 0.588 grams of chlorine per 1 gram of copper. But copper and chlorine also make a sort of bluish-green, aqua blue crystalline solid that has a 1.116 grams of chlorine to 1 gram of copper ratio. So each of these compounds are obviously different compounds. They look different, and they have different mass ratios. Each of these compounds are compounds of copper and chlorine, but let's just see if we can get anything else out of this data. It turns out that if we take a ratio of the ratios, and what I mean by this is here is one of the compounds and there's the other. We're going to take the aqua blue-green color compound, compare it to the green colored compound, and the ratios were 1.116 grams of chlorine per 1 gram of copper to 0.588 grams of chlorine per 1 gram of copper, respectively, for the aqua and green compounds. And this ratio of ratios, notice we can cancel out grams of chlorine and grams of copper, and so we have a ratio of 1.116 to 0.588, which is 2 to 1. And so what ends up happening is that we find the aqua blue compound has twice as much chlorine by mass as the green compound for the same amount of copper. So that's what this ratio of ratios means. And how would we interpret this? Well, one plausible explanation is to note that copper and chlorine are both made up of small units. That's actually something that is somewhat due to John Dalton thinking of compound or elements being made up of small units, which we now know as atoms. And then units of different elements have different masses. So atoms of copper and and atoms of chlorine have different masses. And then what we're forced to conclude is that since the aqua blue compound has twice the mass of chlorine per amount of copper, it must have twice as many chlorine atoms or units as copper, as the second compound does per amount of copper. And so it would look something like this. First compound has some copper and a certain amount of chlorine. Second compound has for each 1 copper twice as much chlorine. And it turns out that that is in fact true. There's twice the chlorine per amount of copper in the aqua blue compound, and in fact the green compound is copper 1 chloride, and the blue-green aqua compound is copper 2 chloride, so CuCl and CuCl2 respectively. And this is an example of what's called the law of multiple proportions, where elements can combine in different ways to form different substances, and when they do, the mass ratios of these different substances are going to be small whole number multiples of each other. In this case, it was a 2 to 1 small whole number ratio, but we could of course have 5 to 3 whole number ratios, or 6 to 5 whole number ratios for different compounds of a given other elements. And that's it for the Chapter 2 screencast on Dalton's atomic theory.